All right, everyone. Welcome to episode 6 of Evans Imagines Negative Mass Antimatter, the one where we talk about experiments. Maybe I should name them all like that. That'd bring in a whole other set of fans. Okay, so first we go over homework from last time. Subscribe, share. I'm getting better at putting that up at the top. And check out my other series that I assume have happened if it's been more than a month from now, which is end of November in 2021. So hello again, everyone. We're getting into the homework now. So first, I've asked you to ring through this paper by Singh from 1986. I've specifically asked you not to get too dragged into the proof, but to just look at the potential that he proves, because everybody accepts the proof. A lot of citations of the proof, for instance, by Nieto and Goldman. And I want you to look at a couple of places that do touch on the proof and how they're citing it, because the proof itself is different from how it's being cited. The proof itself is much more general than the way it's being used by Nieto and Goldman, by Ulrich, Gensura, and other people currently. It could involve positive and negative charges. And if it does involve positive and negative charges, it implies different behavior than is being given in those equations. So I asked you to read Villata as well from 2011, because I'm not the first guy to notice this. Villata did. He doesn't really think there's negative masses, but he points out that for effectively negative masses, you should get the same sort of behavior. I don't have that sort of compunction. But anyway, I wanted you to look at that potential from Singh. I want you to see it for yourself. There's a negative to a power n. So the n is the spin of the charge carrier, in this case, the graviton, spin 2. That's what we're saying from quantum mechanics. And then we're saying that the electromagnetism is different because it's spin 1. So you have a negative sign times everything from electromagnetism. I mean, not everything, but in terms of the sign of the interaction, sign of the field, that's one key difference, right? It's a negative. So where you used to have opposites attract, now you have opposites repel. So that's the situation. And if your model does not meet that physical basis, it is not consistent with the spin 2 model of the graviton, which is the one that people think exists. Think about spin 0 too, because that's another case. The Higgs boson is spin 0. You have to think about, or they think it is, but wouldn't it be interesting if it was spin 2, or I guess spin 0 is another way to say a constant. I have to look this up because this is not the way I naturally think. I'm more of a physicist than a mathematician. So I have to look up what happens with different spins. That's how I found this proof from Singh. Very interesting. Do I have anything more to say about this? I don't think so. Yeah, okay. Don't need to bash Villata, who's been amazing and thought this through very well. Again, another person who I like and doesn't really care much for what I say. Number 2, read Bondi, Wolfgang Bondi from 1954. I think Wolfgang's an amazing person. And explain, make sure this is still recording. Okay, because I'm getting very animated now. Explain his behavior of antimatter relative to positive mass and how that, so that's basically the model that's accepted in general relativity. And I talked about it last time a little bit. If you're paying attention, it's what happens when you plug in a minus sign into just the field equations naturally, even though that's not part of the derivation. That's not part of the domain of the original derivation. So it's kind of an ad hoc, what happens if you plug in a negative sign to general relativity, and then just rationalization upon rationalization after that. So number 1, we agree on some stuff, right? Like the anti-apple should still fall up, but they think that the Earth is chasing it. Like this, there's all sorts of the runaway problem there, and we don't have that problem. Yeah, I'm not a Bondi guy, but unfortunately that makes enemies out of like 90% of the other people in the whole world besides me who think this is a possibility. So I don't want to be enemies, guys. I just don't think the same things you do. Okay, so number 3, read a working paper from Wmap, the Wilkinson microwave anisotropy probe, and explain how we have come how they've come to the current amount of dark energy, dark matter. What are current estimates of standard errors? You can just do part B of that question unless you want to get really complicated. It's pretty complicated, but you can go check it out. It's a good paper. It's a good project. Did I have any point specifically? Yeah, just that it's 96% of other stuff and 4% matter. So we need to make big changes. The other stuff, like I've said before, spans the space, the philosophical space. All models of isotropic differences off by like 70% that way, and then anisotropic differences covering like 26% of the rest. So your model's real broken, mostly isotropically. So I guess that's good in a way, right? It's broken everywhere. kind of a lot. So, yeah, including here. So I think that's going through the homework and yelling about Wmap at you again. The Wilkinson microwave anisotropy probe. Let me get you into a share screen now so you can just read this off the screen. Relevant experiments. Yeah, that's what this one's called. All right, let's present. Let's see if we got any good animations this week. I think I remember I got 1 or 2 in here. Yeah, I told you about this already. Okay. So the stuff that we haven't talked about yet. History of antimatter experiments. I see I fixed some of the background issues, but not all of them. Anyway, so there are a lineage of cool experiments related to our study of antimatter and whether or not it falls up and down, and any matter in general. So 1932, the establishment of antimatter in general, Anderson's cloud chamber. We'll have a picture of it coming up, it looked like, with the massive electron moving in the wrong direction. Thankfully, Dirac had a reason for that. And so everybody like just tacked together, okay, this is right. And it was, I mean, like it's staring you right in the face. You can't misinterpret that. Well, I say as I accused them of misinterpreting that pretty badly. 1963-ish, CP violation of Mesons. I think it's 1964, actually, right? We had that in the last lecture. But subsequently found in all long-lasting Mesons over the next couple of decades. So yeah, all of that, not in the standard model, got to be tacked on, CKM theory. 1980 to present, neutrino studies. So as we get new equipment coming online, we get new problems. So that's good. And we get new information, not always new problems. So neutrino studies, it's a lot of nothing. So far, no offense to guys there. It's just that there's not that many supernova, thankfully, right? I mean, like if there were a lot of supernova close to here, we wouldn't get to hang out there. I'd be like, we would just die in a big explosion, more or less. I mean, probably something more refined than that. Don't get on, don't need any experimental modelers getting on me about how the atmosphere wouldn't die just like that, right? No, it would probably boil us to death, or we would die of hypoxia or something stupid and terrible. But anyway, okay, so then great, that's not getting sidetracked at all. So in 2010, let's see, yeah, we start getting Wmap. So besides the neutrino studies, which are telling us so far, we only got supernovas that are matter. So I don't want to breeze by that. It's a problem for me. Yeah, kind of. People would probably point to it now more than gamma rays, like they used to point to gamma rays, because yes, I should probably include gamma rays on this slide, because that's where you would have antimatter annihilating matter. Yeah, that's a major mistake. I got to put that on this slide. So welcome to me editing this while we're doing it, because this is too bad. I can't let this stand for the future. Gamma rays, man. Too important. Okay, so that's like around the same, it's a little bit before the neutrino studies. 1980s gamma ray studies. Don't find lots of evidence. Patchwork universe objection. Let's put that there, and you guys can go read the Glasgow paper. But can't breeze by that, even though that's not what we're really talking about here. Can't breeze by that on the slide. Very important for the study of our subject. And yeah, so let's see, gamma ray studies. Yeah, so I don't think that's a problem because of the negative mass thing. It would make it so there's a lot less collisions, going back to the beginning of time, if you remember. But yeah, so then we have neutrino studies as well. After that is why I knew we had a timeline mistake there. Then we have, let's see, gamma rays. Great, I got them down there at the bottom a little bit, but I need a little bit more about that. We got the ongoing CERN experiments. Like I say, like there was this really popular, a very nicely produced lecture by Sabine recently, I think was her name. Some professor who was like, I used to think there was antimatter or anti-gravity, and that's why there was dark energy. I'm paraphrasing because I didn't listen to all of it, because I don't like anti-gravity people, man. That's not what we're talking about. We're talking about regular gravity with negative mass antimatter. It's a different thing. Anyway, and my thing's what a graviton comes from, and your thing is just what? Anyway, but it came up because she cited the alpha experiment as well. She doesn't think it's right. Dude, you need to read that experiment again, because yeah, okay, look at this range of study. The initial alpha experiments, to me, are an example of extremely underwhelming performance, because they proved you know, the thing that Eötvös had established, the equivalence of the inertial and gravitational mass for matter, right? That's the subtext. We've only done it for matter systems. But, you know, people will cite vacuum pairs as an objection to that. And that's okay if you think both parts of the pair have positive mass. If you think that the net pair has 0 gravitational mass, you still don't have a problem. Backing up, not getting mad at random quantum field theorists who are definitely not watching this and definitely not getting mad at me, but you guys could see that, the passion, right? That's the whole point. Okay, but look at this ratio, right? So I think it's -1. The standard model thinks it's 1. The experimental ratio that's decided between these two things for whoever this study was, I can't believe you would even put it up there, but was -85 to 115. So yeah, I mean, I guess 1 is kind of like closer to the middle of this range, but what kind of like, we don't have no certainty in these results. We don't have enough antimatter yet. We knew that. We got sidetracked looking for Higgs because we wanted to pat each other on the back and stuff instead. And I mean, you know, it was good. It was a good moment for science. We had another time. Science traditionally, for the last few hundred years, has proceeded through the glorification of Englishmen. Don't know why. Don't really understand it. Doesn't really make sense to me. But we had another moment, and that's what made this moment so special. White guy, Higgs. I mean, to me, that's rude to say. But if this was such a good idea, you wouldn't keep calling it the white guy name. You would call it the underlying thing. And I think the reason that they don't is that it's really complicated and it's not that convincing to an average person. But what is convincing to the average person is, white guy, right? Another white guy. So that's why we're bringing him back, like Boyle and Charles and Gay-Lussac and stuff, and things where you just got proportionalities and science isn't that great, really, right? Or now, like, okay, I'm gonna kind of bash the Higgs boson in a couple of moments, with the downside that I don't really know what to a positive replacement yet. I don't really have that figured out. But I like to bash. That's like my whole thing, right? You can see if I'm good at anything, it's questioning the right bit of conventional wisdom. I think everything after that, you guys are on your own. I'm not a mathematician, as any number of mathematicians, I'm sure, would be happy to tell you. Okay. I did have a good thing on the a Millennium Prize, though. It turns out that Yang Mills Millennium Prize is related to the mass gap thing. I got some good thoughts on that. Not for this class, but I got a good one. Okay, so here's a cloud chamber. Back on track. So this is what they were looking at. And like I was telling you, not super mathy what we're looking at here, right? I mean, like I said, one of these lines, bendy, pretty bendy, come out pretty bendy. That's it. That's the whole observation. That and a comparison line that is less bendy. And that's all you needed. I mean, I'm not sure it's on this slide. I've hand waved at some specific line, but the bendiness proportionality is what we're seeing here. And we should see more of gamma rays, right? If there were a lot of antimatter seeping here. So honestly, not great that there's any of it, right? Because it should be colliding with things before it gets here, even from the sun. And so I think the idea is there's been collisions and stuff, or I don't really know, infrequent collisions for some reason. But regardless, I don't think we've got a big seeping bunch of antimatter like getting here somehow, right? So that's the reason I'm not worried about the lack of gamma rays. I don't expect them because we've got repulsion between the galaxies. That means we have double the escape velocity. So you should have, is it half or a quarter? I don't know, something like that of the amount of collisions. There also probably should be a distribution of those collisions. So hey, if you're a particularly enterprising student, you can figure out whether or not the frequency distribution of gamma ray bursts corresponds to the distribution of sizes of asteroids. If it does, bada bing, you got yourself a paper, and just say a thank you to Evans Imagines or something, because it's a good problem, right? But I'm not gonna solve it. So, all right. I mean, it's not even on my 5-year plan. That's just a fun one for you guys who are better at math. Okay, so CP violation, meson studies. Why are mesons useful? Come on, guys. If you haven't watched this class yet, go back and watch. Is it the last one, the one before that? Whenever I was talking about ML Good, I think it was class 5. So go back. ML Goods will be acknowledged in my lifetime. I love this guy. It's a quark and an anti-quark living together. So held together by the strong force. I say living together. You know what I mean? They're a little particle together of a quark and another quark. newsflash, regularly they're living in threes, right? So we're not getting a lot of these. They're decaying pretty fast in general. So we don't see mesons lasting forever. These are generally decay studies that are happening, then they've lasted a very short amount of time. But we've talked about muonium, positronium, the quark and the antiquark are even closer. So whatever they're feeling, I mean, it's not really the repulsion between them, right? It's the difference between them, because I mean, they are also oppositely charged. So that's the bigger deal. But if you're talking about the, the charge thing is like 1,000, it's way, way, way bigger, and it scales with the exact same scaling as electromagnetism, or as gravity. And so gravity is always going to, or the electromagnetic force is always going to matter more than the gravitational force. It'll be a tiny correction at best. So yeah, it's not to do with the binding of those things. It's to do with their decay and stuff like that, their stability, absolute stability. Yeah, so I think that this was really amazing. Best thing since Einstein's mass energy equivalence, which I've been reading some Ohanian now, and it might be more of the Lau/Klein equivalence principle, comes from the conservation, and then some nice Gaussian applications thereafter. I think that's a much more convincing argument. Okay, so neutrino study is not my argument, by the way. I got another argument there too, but those historically are definitely the better proofs than Einstein's. No offense to Einstein's, just, he's not a math guy 100% either. He was a patent clerk and a tutor and eventually physicist. If supernovae are far away from antistars, they should have an neutrino signature. So I've made the contention at times, and I do believe there may be some of the furthest visible stars are made of antimatter. We don't have data anywhere near conclusive about that, because the furthest visible stars are like megaparsecs. And I've told you before, how far away is it, class? How far away have humans sent a thingy? Because that's how far we really know we can go. That's how far we really know our approximation holds. 0.0000000000752. I don't know the next part, but it's that many zeros before you get to the length humans have traveled, and we're extrapolating it to 5. The number 5, 5 point all of those zeros. So that's the kind of thing we have, these coincidences and numerical coincidences that I think are ridiculous. So I do not believe in that numerical coincidence, and I think instead that it's just everything came from nothing, and so there's an equal number of stars and antistars. And yeah, most of the ones here are stars, and you can be happy they are, or else it would be a really hot place to be, and probably wouldn't be no dinosaurs or people or nothing, right? I mean, it'd be like a binary galaxy or something. You'd be going and nothing alive for sure. We would see like, crazy signature far away and go, whoa, don't go there, right? I mean, like nothing could be, I mean, conceptualizing the kind of thing that would have to live in a quasar or whatever would be. Pulsar, those are fun astronomical objects. Cosmological people are wonderful to talk to, so I guess I should think more about these blazars. Blazars and quasars, some of the biggest, highest energy objects in the universe. It's been a long time, so why are these things still around is a very interesting question to me, and probably to all the Hoyle Narlikar people as well, but I'm not a Hoyle Narlikar guy. I just love Narlikar, okay? He's just a very interesting guy, wrote some very good books. Go to whatever discipline you're in and read the old Russian authors in it, 60s and 70s, find a good guy. There's definitely a guy with good humor who maybe illustrated his own books. Find that one. Narlikar is the guy in particle physics. Okay, downside, neutrinos have a, downside is hard to find neutrinos. I think that is, we have the Dune and Super K I've been talking about, and you're probably thinking, oh, these physicists, they're so smart. What have they done now? Well, you know what Dune is? Deep underground neutrino experiment. You know what used to be under there? A mine. You know what they did? More or less pipe in a bunch of chlorine. And so, I mean, it's not as pretty. They don't show pictures of that because it's just mine chlorine, right? And they just listen, beep. Oh, I got a beep. Plus or minus a few beeps, whatever. But Super K is a much more beautiful version of that in Japan also. Even though Dune, I think, could get better than it soon, or maybe is about the same always. This is beautiful, right? I mean, like, look at these guys in a room full of like chlorine aquariums, plus or minus. So they're just sitting there waiting for neutrinos to happen. And when there's a bunch of neutrinos together, you're assuming that far away, and I mean, see how it's a sphere, right? So you get ding, 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 ding. And eventually, if you get a few of them, and you can interpolate a direction that they came from and kind of the speed they're traveling at, and correlate with an event maybe you saw on a different kind of device. So that's what's going on here. Wmap. So yeah, I should say I have in the past talked about these neutrino studies, and my point has been the reason that to me, even though yes, we have not seen antineutrinos from an anti-supernova, the reason that even though this is a very impressive experiment and looking at exactly what I care about, I am not convinced to the contrary, is that I do not expect them to happen so close to us. I do not expect there to be antimatter supernova. Number one, supernova don't happen that close to us. Number two, antimatter stars are not that close to us because our galaxy cluster is held together by gravity. If it wasn't held together by gravity, maybe half of the galaxies in the cluster would be made of matter or antimatter. But I think that probably the cluster level is where you're held together. That's the largest gravitationally bound unit is the clue. It says that's the level at which you have more or less mass segregation of like mass. So therefore, we got to go a long way, a lot further than we're looking. I mean, now if we're letting neutrinos be Dirac and evidence of an anti-supernova, then we do actually see pretty far, like almost a megaparsec, like 0.00000 whatever is how far we've traveled. Neutrinos allowed us to see 10 times or 10 to the 10 times as far, much, much, much further. So neutrino guys, hey, I've used you as examples every now and again. I think you're fun guys living deep underground, but you do great work. This is important. You might find an anti-supernova. If you do, you can email me at boney@alum.mit.edu. I will back you up. I will give you a pat on the back. I will give you a beer, whatever. I would love to find that data point. I expect you to find it soon. You need a kind of big one, right? It's not going to be a 1A because, like I said, they'd have to be within 1 megaparsec. But not every supernova is a 1A, right? Some of them are big boys. I haven't looked this up recently, but this rant has a corollary that every 30 or 40 or 50 years, you might see a big one from further away. And so if you get a big one that's from 10, 20 megaparsecs, then you're outside the cluster. And if you get a supernova from outside the cluster where you're seeing neutrinos, then you need a different explanation for what's going wrong. Or you can just admit that you're wrong, which is possible. I'll admit, like we got dozens of crucial experiments here we're talking about. So, probably way more likely I'm wrong than I'm right, but still enjoy my YouTube series and subscribe or whatever. Now, this is just fun. Let's see. Wmap. So we talked about this before. It's kind of where the standard model is eating itself. Like they've tried to explain everything and they've come to here where we got a problem and it goes back to the beginning of time. And like the further we get away from here, the less good it is. And like the mistakes are everywhere and locally. And so like the ones that are everywhere, we call dark energy. The ones that are localized, we call dark matter. Well, we got just mistakes everywhere. And that's not what you're looking at here. Exactly right. Wmap is just beautiful. This is not an example of where the mistakes are. This is just an example of one representative cross-section from Wmap. And I believe this is the anisotropies are being called out specifically. Yeah, so I'm not going to dwell on this. I feel like I've dwelled on this at specifically like way too much for you guys. Now here's a new rant for you. And this one's super undeveloped. So if you thought my other larks were really ridiculous, well, here's this one. Higgs, everybody likes Higgs. Well, you're dumb. That's basically this rant. Okay, so the Higgs field, I think, is basically exists because gauge field people love it, which I love gauge theory. I've talked about, electroweak unification being a clue. We have to do everything that way. But that doesn't mean you can just make everything a field. And I agree. If you did make everything a field this way, you get the result you get. But it doesn't help with negative mass, first of all, because this construction, it has a square proportional to square relationship underlying it. Again, at the very start, the Higgs field here is squared. So you would take the square root of a square and have a plus or minus sign immediately in question. So you have to deal with the negative Higgs is the just one Higgs and is a negative sign in the interaction field. Who cares? You decide it however you like. There's probably different philosophies here, just like there was in quantum mechanics. I'm not going to insist on your philosophy. I just want you to see what you're doing is being more comfortable with the thing because you made it into a field. Fine. If that makes you more comfortable, feel more comfortable. Not to me. I mean, I'm happy that it kind of extends mass into the electroweak theory as things that are explained by gauge theories. That's cool. I don't like, though, new fields that come from, you know, come from where? I don't know. So it's like, I don't like God particles because I don't like God. No offense, God, you've given me a very nice life. And then, shake my fist at you anyway. Okay, so these were CERN energy sources to produce tiny CERN, blah, blah, blah. Yeah, so I've talked about these a lot at length. There are 3 of them. I think it's cool that there's like a race. There's like a bunch of dudes in Europe who really care about this, who probably all think I'm wrong, and that there's really only just chasing down a boring result. But, you know, in the next 5-10 years, you know, what are we talking, 2020? By 2030, we should probably have a sigma or 2. And it might come down that I'm wrong or that I'm right. And if I'm right, you're probably watching this video. So, hey, welcome to my weird bedroom from 2021. All right. So, cosmic gamma ray backgrounds, gamma ray studies. So the cosmic gamma ray background is the equivalent of the cosmic microwave background for this part of the spectrum. So like I say, like the stuff we were getting from satellites is new. This is even newer. This is like higher energy stuff we need longer to collect. I still need to do some simulations. Yeah, hey, I gave you one of you guys one of this earlier. Like this, do you get a distribution of asteroid velocities with the how does that match sizes versus how many would have escape velocity? Do you get that resulting frequency of collisions coming from other places? If so, you might be seeing the right result, not the wrong result. Oh yeah, another thing is we can think about what happened all the way back to the beginning of time, right? Because we now have the mechanism for inflation, which was the repulsion of things, right? The repulsion of, so my thought is that initially, before the visible beginning of time, because like there's a problem of collisions initially making it blind when it's really, really, really dense. Can't see in there, right? Plus or minus. So I'm saying that we had initially some condition that's more or less little circle or sphere that's populated with a bunch of stuff that came from some sort of vacuum fluctuation, uniform vacuum fluctuation. Then a bunch of annihilations start happening. Almost everything annihilates, right? Just explosions, nothing but like alpha and anti-alpha particles. And then eventually you have the situation where stuff is kind of further apart on average than it was because of all of these annihilations, right? Like it's almost all of it's gone. 99.99999. We're getting some more zeros here again. It's gone. And so what you wind up with is, oh, some stuff. Oh, some stuff. Whatever the local slight difference was becomes amplified because what used to be positive slightly has now become only positive. And what used to be negative slightly is now only negative. And so, you know, these things, they have big explosions and they do larger agglomerations of this, but eventually you wind up with only positives together and only negatives together. And you get them far enough apart eventually where the holding them together force, whatever it was, don't know that one. I mean, this is back beyond what we'll be able to see. So you can have a philosophical choice. I have my own ideas, but that is overwhelmed by the R squared one, the gravitational repulsion of the little tracks. So I think that's a pretty convincing explanation of why we have the baryon to photon ratio that we have. I've been calling that boson like a real bozo. But yeah, so you can read more cosmology from Weinberg. I added this after he passed recently. So yeah, I'm going to have a little slide, I think, on him. Just a little excerpt from our correspondence where I tell you he didn't like this. I told you earlier, 2 out of 3 out of Glashow, Weinberg, and Salam have weighed in with a on me. So he specifically said, I wish I could, I would have been nice and said, I like your book, blah, blah, blah. I wish I could be encouraging about your idea, but I can't. But yeah, so I brought up that there's probably no direct evidence yet until the CERN experiments. But he brings up that it violates the equivalence principle. Number one, it's a problem for the old school guys. That's fair. Number two, what would you say about particles that are on antiparticles? These are the same list from Feynman, right? Like these guys have, they're sharp, man. This guy was amazing. Can you believe this Nobel laureate gave me the time of day, much less gave me 3 counterexamples, right? That he thought were counterexamples. And that's awesome. So, I mean, like number one, indulge the thought came up with 3 thought experiments: violation of the equivalence principle, particles that are their own antiparticles having the same deflection. Doesn't think about the exact mass being the same. But, you know, the really, really indulged me a lot, thought about this for a while. So I wanted to say thank you so much. But I do think we have a problem here. The Nieto and Goldman problem is becoming metastasized, and we have to make sure that everybody understands Singh's result is just that we have a negative applied to the other field sign, as when we relate the attractive versus repulsive charge relationship for electromagnetism and gravity. So gravity charges mass, negative mass is a negative gravitational charge in this model, in the comparisons. Okay. So RIP to Weinberg, and he did not have favorable things to say about the theory, but indulged it. So I appreciate that. And I mean, yeah, it's the standard model does not agree with this. So go read somewhere else. Actually, I probably will do a standard model bashing / reviewing slide that's a little better than my quantum mechanics foundations. So MAGE, the muonium anti-gravity experiment, pretty awesome. We don't know whether or not it floats. We don't know about it for positronium either. It turns out muonium lasts longer, it's bigger. So you have to interpolate a little. You have to figure out maybe something can be done with the annihilation rates, transition states, maybe with a vibrational state. That's a wink at my thesis. It's not, nobody cares about it anymore. Okay, so I wanted to now talk about supporting arguments. Who cares about them a little bit? We'll probably talk more about this in the future. But I think at this point, I've talked a lot about the experiments, how they might show us to be wrong or right. And specifically, most of the supporting arguments for negative mass antimatter are only for this theory. Number 1, supported by graviton symmetry. Number 2, it has dark energy as gravity, but that's the same. CP violation explained, early cosmological model, maybe a photon baryon ratio. Wow, I'm not going to publish the Singh boson. We're going to fix it. This is what you should do when you make a mistake, even if you're in the middle of a presentation. You say, yes, I remember I made this mistake earlier and I fixed it. So it's baryon, not boson in this context. Duh. Sorry. Motivated hyperinflation. Regions are closer together earlier. So now that's why the effective cosmological constant, blah, 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 used to be higher. These guys have so many free parameters. We don't. The jerk prediction, negative jerk. Alternative explanation for antimatter rather than going backwards in time. So I think we got a lot of stuff here, and that's just with this negative mass antimatter that follows spin to graviton symmetry. So we got a couple things that do bother me, and one of them was what Weinberg just brought up. Why does the photon follow only one geodesic? Well, number 1, we haven't seen them go by anti-planets very much, or anti-stars that we thought were anti-stars. So, and if they did, I'm still not sure that would be deflected differently, because I think every positive or negative mass star would have a positive inertial mass to traveling light. And so, I mean, traveling anything. And so it would deform space the same direction. In that approximation, which it's unclear to me whether or not is valid more than locally. Now, granted, the locality of this 0.0000007 megaparsecs, which we inhabit, is very important to us personally, but we can't let that determine our physics. So I think that it's possible that photons don't follow one geodesic, and that's only a local view, and it's true locally, and that is not true in a broader way. I don't really have a replacement for it though, so that's why it's on the bold list. And then something that Griffiths pointed out, CP violation differs in magnitude across mesons. Yep, but also they're measuring it differently. I don't know anything about mesons, so, you know, like aside from that, they're a convenient model for me to make, you know, pronouncements about. I'm going to make a Klein-Jordan transition element. Nothing fancy. I can't do the fancy part. If you guys are fancy guys, please. But then we've got a lot of other disagreements where people will bring them up, and you should know when they bring them up why they don't bother me, and if they bother you, fine. Where the neutrinos, like I said, I think they're outside the cluster, and so we can't see there, so fine. Also, they might not be Dirac. I'm not convinced that neutrinos have that little bit of mass that everybody claims they do from neutrino oscillations. Doesn't seem like a good explanation to me, because we got some similar problems there. But yeah, so if they are Dirac, we should see them from anti-supernova. If they're not, then everything's going to look the same. Anti-supernova and supernova are going to look the exact same from stars and anti-stars, just like their light looks the same because it don't have mass. So disagrees with Einstein and Bondi, doesn't respect equivalence principle. Yeah, right. The future. Welcome to it. Sometimes stuff's going to have to get overturned. And particularly, I don't mind disagreeing with Bondi because that was such a slapdash theory. All right, so Eotvos, misunderstandings. A lot of people seduced by the many digits of the Eotvos experiments. It's number one for Feynman. It's number one. Nope. Credit to Weinberg. Credit to Weinberg. Credit to Weinberg. Yeah, doesn't talk about that in his objection. So he didn't bring up Eotvos, even though, because it's not correct as an actual refutation of my theory. And neither did Griffith. So that's nice. But a lot of people, Feynman, for instance, brought this up, and they are seduced by Eotvos arguments, particularly in whatever so Feynman liked virtual pairs, right? So he thought about whatever experiment amplified the effect of virtual pairs the most, and cited that one, even though it was immediately irrelevant. And so it's very hard to understand what he's talking about with those K electrons in iron. You can go look at that. I think that was second or third lecture. Gamma ray questions. Like I said, open-ended. I expect about a fourth as many to happen across, integrate across all wavelengths. So yeah, I think it's an open question to me if this analysis done in the patchwork universe by Glashow, Derugala, and Cohen, if that would still apply with negative mass calculations in either the Bondi or graviton type. I don't think it does in either case. I think both are fine. And yeah, I should say, I don't think the Bondi guys are provably different from me yet. So, and maybe ever, because their antimatter would be in the gaps, right? If you have repulsive antimatter that repulses even itself, it maintains a very low density forever because it can't get together. And so in its low density forever, good luck looking for it to all of you. That's the way I feel about it. I don't like my antimatter to be good luck looking for it forever. I want to look at it at night and say, there it is, the antimatter. So that's why I like mine. At its core, there it is. Yeah, I'm using the artifice of the graviton and all that, but I like it that I could see an anti-star is definitely part. And it would explain why everything on the whole doesn't appear to be moving anywhere, right? Like, because we got to push and a pull and they're about canceling out. And maybe if everything came from nothing, they would exactly cancel out. And it would look real much like it does. Okay, so lack of direct observation. Hey, even Weinberg gave me credit for that. Everybody will. Like, right? Einstein, I'm calling Feynman Einstein. So there you go again, my idols. But Feynman did say that the CP violation in Mesons, the lack thereof, was the most direct evidence. And now that's in favor of negative mass antimatter, right? Because we found CP violation. So at best, we got lack of direct observation. I kind of think we got direct observation that showed I was right. Unfamiliarity of, so yeah, that's not only in the I don't care about it, it's in you're wrong territory. So maybe I should add a new one down there. Unfamiliarity of antimatter. Yeah, people just don't see it and they don't think about it and they like it that way. And fine, I mean, I guess. Higgs focus, yeah. They would just get lost in the weeds and not recognize this is something they've built for themselves to be happy about mass as field people. But like I say, you just make m squared proportional to phi squared and you figure it out. It's not hard. Yeah, we talked about that. And yeah, I learned something recently, so I just wanted to point this out. That the way that we know about interplanetary dust is looking at the horizon before sunrise. So go look out there at the sky and just like wonder. And sometimes you'll see stuff. The other night I yelled about the stars. Like, the star is crazy. It's just Mercury. Like right after sunset, Mercury was really high in the sky in winter. And I wasn't used to that. And so I yelled about it. But I was like, you guys got to check this out in Orange County, see if it's still there. I don't know where the star is. Something weird about this. I thought maybe we're seeing a supernova. I'm going to see it on the news. Maybe it's the first anti-supernova. Be ready my whole life, man. I'm looking up for that. Oh, also this week in Southern California, we did not get to see the big solar eclipse that happened because, yeah, it was cloudy for the first time in a month. So Look, can you imagine if it was back in the day where that was like the confirmation of your entire theory hedged on you seeing the solar eclipse that you predicted and it was cloudy? And I mean, maybe you could hop on a train in the nighttime. I don't know. So you got to get some good, accurate weather forecasting and have trains. And oh man, I just can't imagine having your whole life ruined because of a cloudy day. But I did think about it after I woke up in the middle of the night and it was cloudy. I thought there was more to my slides, like giving you homework and stuff. So I'll wait for it to catch up. I've clicked the button a few times now. I'm probably, let me check on the battery on the, okay. My battery's almost run out. But for next time, we still have a little bit of time for me to tell you about this. I want you to go into what is the difference between Dirac and Majorana neutrinos? How far away can the current or neutrino detectors reliably detect? Look it up yourself for Dune, look it up for Super K, figure it out. You got to look in the weeds a little bit. Standard 1A supernovas, think about what other types of things you might see and should you see antimatter from that. Read about MAGE by Professor Kaplan and Phillips, I see is on there. Expectations of a bound state for equal positive and negative mass from a gravitational mass perspective. What's the reduced mass? Where do we see the reduced mass affecting potential? What do we expect from that experiment? And then read the oldest reference to antimatter from 1898 in Nature. This is a good one. It's only cited sometimes, but a mathematical Nature walk or something is a very beautiful idea that this guy had 1898, I think it was. And yeah, right. And it's just a nice little, he was the same thing, going home for the holidays or something, wrote a nice little poem about what if there was an exact opposite of all the matter that we know, and went through basically CPT symmetry. It was really awesome. But I wanted you to look through your own culture or your own, just can you find an older reference or something like the idea of yin and yang, right? Like there's yin and yang, whatever. There's got to be some other culture idea that has gotten more developed into a theory of the cosmos that bore some fruit. There's a lot of fruit here that's pretty low hanging. So let me know if you find something. Again, boney@alum.mit.edu. And that is the end of this lecture. I think it's our longest one yet, so thanks for sticking with us if you did. And thank you for joining us on Evans Imagines. Now for the part where I figure out how to turn it off and then say bye-bye.